Hello, this is the TMUA from 2017, paper 1 specifically of the TMUA from 2017. And this is something new for me. I've not done a TMUA before. I've been hearing a lot about them, but most of the papers that I do are physics related. I mean, I've done all the math papers and I've been going through the step papers when it comes to maths. But TMUA is a new one. So I'm going to start working through all of these, and I see we've got 75 minutes here. You get 2 papers every year, 20 questions on each paper, and 75 minutes. So it's a little bit longer than an ESAT or a NJA, something like that. So I'm assuming the questions are going to be a little bit more difficult, but still 20 questions in 75 minutes. They can't be that difficult because that's a lot of questions to fit in. That doesn't mean to say I'm going to get them all, but we'll see how it goes. Calculator's not allowed, but so what? I don't really use them anyway. And who's turning up with a dictionary? That'll be a bit on the strange side. So this could be quite a long video, this one. I don't really know how long it's going to take. It's sort of heading a bit into the unknown. Right, question 1. Given that dy dx is that, y is that, x is when x is that, find y in terms of x. Okay, right. So let's split this second fraction, just get a clear look of what I'm integrating before I dive in. So that's going to be a plus where the x's are going to cancel. So I'm just integrating that. So that's going to be an x cubed. This will be, well, the minus 2 is going to come from the x to the minus 2. So that's going to work. And then that will become a minus 3 over x plus c. Okay, right. So we've already got quite a lot of them ruled out, and all of this is already looking like one of those two. Well, actually, in fact, it already looks like C before I've even done anything here. But anyway, let's put in these values. So 5 is equal to 1 plus 1 minus 3 plus C. So C is 6, which again fits in with C. Right, okay, that didn't really need to work out C there, because by the time you've actually got these 3 bits, that only matches with C. So, yeah. Okay. Right, question 1 anyway, that was fairly standard, but the first question off it is on these sort of papers, isn't it? Question 2, function f is given by that. What's the value of the second derivative when x is 1? Right, okay. Right, it's bracket squared, lots of stuff. Might as well expand that, because if I don't, if I'm differentiating that twice, I'm still going to end up with brackets, aren't I? So I think I will expand. 4 over x squared plus 1 over 4x to the 4. And then I'm going to have minus 4 over 2x cubed. So minus 2 over x cubed. Okay. So differentiate this twice. So that's going to be minus 8 over x cubed. That will be minus 4. So the 4's will cancel. So minus 1 over x to the 5. And that will be plus 6 over x to the 4. Go again. That's now going to become a plus 24 over x to the 4. Then I'm going to have a plus 5 over x to the 6 and a minus 24 over x to the 4. Oh, x to the 5, not x to the 4. Yeah, all that stuff on the bottom doesn't matter, does it? Because I'm putting 1 in. So it's just going to be 24 minus 24 plus 5, which is C again. Okay, another nice one to get us going. The question 3, a line L has that equation. Second line is perpendicular to L, passes through the point minus 6, 0. Find the area of the region enclosed by the 2 lines and the x-axis. Okay, so we're going to be on positive y. It's going through minus 6 at one end of the triangle. It's going to be, what, 3 at the other end. Right, so I need to put my axis a little bit off centre here, because we'll be going through here and here and here. So that will be our original line. This will be the perpendicular line, and so that's our right angle. So this is our y equals 6 minus 2x. So this one is going to be y, well, minus 0. His gradient will be a half, so a half of x plus 6. So I need to get the y value here, don't I? And then I'm all set up. So that is going to be, well, let's say 6 minus 2x. Well, actually, I'll double that. 12 minus 4x is equal to x plus 6. So I've got that 5x is 6, x is 6 over 5, which means that y is going to be 6 minus 2 and 2/5, which is 3 and 3/5. And then I need to multiply that by 9 over 2, which is half the base. So I've got 9 over 2 times 18 over 5, which is 81 over 5. So that's 16 and a fifth. A. Oh, okay. That was a bit more interesting than the first two. Question 4. When that is multiplied by that, the resulting product is divided by that, and the remainder is 24. Right, remainder theorem. So if we're dividing by that, we've got to put -1 into these two things multiplied together. So I'm going to get, what, 3 minus 8 minus 3 multiplied by minus p minus 1 is equal to 24. So that goes, divide that through, -3, add that on, -2, p is 2. Right, remainder theorem is a bit there, but they're quick. 5. S is the complete set of values of x which satisfy both the inequalities that and that. The set S can also be represented by a single inequality. Which one of the following single inequalities represents a set S? Okay, right, well this one's easier to deal with, so that just needs x being greater than 4. This is x minus 6, x minus 2. So positive quadratic below the axis, so it's between those roots. So we need to be, well, greater than 4 here, but we need to be less than 6 there. So we want to be between 4 and 6. That's what we want. And all right, they've written these all out as annoying things. Right, well, it's not going to be that or that. What we got down the bottom, we've got straight ones. No, we haven't. So it's not going to be either the ones down the bottom. So it's going to have to be some of these ones. So 4 and 6. So we're going to have the 24s and the 10s. Is that going to work? So I want it to be, so I'm going to have x minus 4, x minus 6. And it's positive, so I want it between the roots. So it's going to be C, isn't it? Because yeah, expand that out, -10, and I want it below the axis. So yeah, C. Okay, got a bit fiddly towards the end, but not bad. The tangent to the circle x squared plus y squared is 144, passes through the point 20, 0 and crosses the positive y-axis. What is the value of y at the point where the tangent meets the y-axis? So we've got tangent to that circle, passes through that point. So we're all positive quadrant here, first quadrant. So I've got a bit of a circle there going up to 12. And then it's going through here at 20, and it's tangent to the circle. So I've got a line like this, and I want to know here, this value on the y-axis. Okay, so I've got this circle, this line is tangent, so we need to get them to intersect at one place. So I need the equation of that line, which I don't know because I don't know the gradient, but at least that's only one unknown. So that line is going to be y minus 0 is going to be mx minus 20. Okay, so sub that in, solve for m when there's just one solution. That's got to be the way to go, isn't it? So x squared is m squared, well, just expand this, I've got to expand this bracket, I've got to square that. So x squared plus 400 minus 40x. Oh, I've got to equal to plus equals 144. So I'm going to want to get the discriminant to be equal to 0 on this. So b squared, what have I got for x's? X is just this, isn't it? It's minus 40. So my b squared is going to be 1600 m squared. Oh no, m to the 4, sorry, because I've already got an m squared. So that's 1600 m to the 4. And then I need to take off minus, oh dearie me, right, so minus 4 times, so my a is 1 plus m squared, and my c, oh, this is horrible. Am I doing this right? Anyway, 400 m squared, I'll see how bad it looks when I get to the end, and then minus 144, and that's got to be equal to 0. Well, I mean, I suppose I can get rid of a few things, can't I? I mean, I can set these equal to each other, get rid of that 4, make that a 400. Let's go for, let's get rid of, turn this into a quadratic. So let's say that m squared equals s on this. So I've got 400 s squared equals 1 plus s times 400 s minus 144. Okay, so that is 400 s squared equals, oh, that's nice. I've got the 400 s squared is going to cancel, isn't it? So 400 s plus 400 s squared minus 144 minus 144 s. Right, so they go away. And then I've got that 144 is equal to 256, nice number, s. Yeah, that's good, isn't it? So s is m squared. So I've got m squared is 12 squared over 16 squared. What am I'm trying to get? What am I even trying to do? Oh, I'm trying to get this value up here. So I need to do minus 20. Oh, I want the positive, no, I'll go negative root of this. This is a negative gradient, isn't it? So m is going to be minus 3/4. And then I need to multiply that by minus 20. So I'm going to get 15b. Right, that was a lot more difficult than the previous questions. 7. The first 3 terms of an arithmetic progression are those. P is less than 0. And the first 3 terms of a geometric progression are those. Find the sum of the first 10 terms of the arithmetic progression. Oh my word, right, okay. So I've got, so for the arithmetic progression, I've got P, Q, and P squared. So that is P plus D, P plus 2D. And then for the geometric progression, I've got P squared, Q. So that is going to be P times R squared. Okay, so this is telling me then that P is equal to R. So that's nice. And then that means that Q is equal to P cubed. Okay. And what do I want on all this? I want to get the first 10 terms of the arithmetic progression. So that's going to be 10 lots of the starting value. So 10 lots of P. And then I'm going to have 9, well, the 9th triangular number of differences, because I've got 1D plus 2D plus 3D. So 9th triangular number is 45. So I want to do 10P plus 45D. Okay, so P plus D is equal to P cubed from here. And then what else can I do? P plus 2D is going to be equal to P squared. Okay, so that seems fine, doesn't it? So I've got that. Which way am I going to want to go about doing this? Well, D, I suppose I just get D from the first one, put it in there. Seems plausible, doesn't it? So I'll have P plus 2D, so that's going to be plus 2 lots of P cubed minus P is equal to P squared. Right, so I should be able to get myself a P out of all of this. So I've got 2P cubed minus P squared minus P is equal to 0. P is less than 0. So I can get rid of a whole load of p's on this. So 2p squared minus p minus 1 is equal to 0. So that's going to be, I'm taking up so much of the screen here. 2p, I've got to have a minus 1, a plus 1, another p. So p is 1 or minus a half. So it's got to be minus a half because p's negative. And then I've got to get what D is. So where am I getting D? What's my quickest route to D? Well, P plus D is P cubed. Is that going to be what I want? Yeah, probably. So D anyway. D is P cubed, which is minus an 1/8 and then minus p, so plus a half. So that is 3/8. Okay, right, so that's all right. So 10p plus 45d is minus 5 plus 45 times 3 over 8. God, these are horrible looking things. So that's what, 135. Well, they're all over 8, the answer. So 135 minus 40, so 95 over 8. Right, they've certainly stepped up the difficulty on these in the last couple. Find the complete set of values of x with x between those that range 0 to pi inclusive, for which that is positive. Right, okay, this should be a bit easier then, I think. So we either want both of them to be, I mean, they're given so few blinking numbers here. I'm thinking maybe this is just gonna, I'll just look at these answers. Anyway, we either want them both positive or both negative. So if they're both positive, then we need, so let's write this down so I don't forget what I'm doing. So both positive, so we need sine x to be less than, oh, we can have or equal, so less than or equal to a half. So that's keeping it in that range from 0 to pi by 6. Oh, I suppose we've got the other end, haven't we? We have got the other end. So 5 pi over 6 to pi. And we need cos x to be positive. All right, so that doesn't fit with this bit because we need it to be in that first quadrant for cos x to be positive. Right, so we've got this bit, so it's going to have to be A or B. It can't be either of these because we know that that and that are fine. So that means it's going to have to be A, isn't it? Because I've already ruled out B by saying, well, it can't be that bit. I've just crossed it out there. So would that work? That's where we've got, if we're going just past pi by 2, so sine's going to be negative, cos is going to be negative. So yeah, A. Right, a little bit of deduction there, but yeah, it was quite handy that this bit that I crossed out here happens to be the second option in B. So yeah, that made things a bit easier. Right, back on circles again, right? So question 9, a circle has got that equation. Regular hexagon is drawn inside this circle so that vertices of the hexagon touch the circle. What is the area of the hexagon? Right, so this is x minus 9 squared plus y minus 11 squared. So I need to take off an 81 and 121. And then I've got the 178 there. So what have I got on all of this? That's 202. So I've got 24 all in all. So let's get rid of all of that. So it equals 24. So I've got some kind of circle which has got a hexagon in it. So the hexagon's going to be splitting this into 6 triangles like this. These are root 24 sides on these. So I'm going to do, well, and we know they're 60 degrees. So the area of each one of these, so half AB sine C. So I've got a half times 24, because I've got the 2 root 24s. And then sine of 60 degrees is the root 3 over 2. And then I need to multiply that by 6. So that's going to be 36 root 3, which is F. Right, that was a really nice question. Quite happy with that one. Again, it sort of sped up a little bit in the last couple after getting bogged down in the previous set. So question 10. Oops, hit the scroll bar. Right, question 10. A curve C has equation y equals f of x, where f of x is that. P is real. Gradient of the normal to the curve C at the point where x is minus 1 is m. What is the greatest possible value of m as p varies? So the greatest possible value of the normal at that point. Right, well, we're certainly going to have to get the tangent anyway, so let's go about differentiating this. P is just some constant, so that goes away. Minus 6p squared, and we've got plus 6px, then minus 3x squared. And we're dealing with x being minus 1, so f dash of minus 1. That's going to be, well, still minus 6p squared. That's going to be minus 6p, and that's going to be minus 3. So that's giving me the gradient of the tangent. So I want to do minus 1 over that. So that's going to make everything pluses. So that certainly helps. So 1 over 6p squared plus 6p plus 3. So we want to maximize that. So we want to minimize this thing on the bottom. So we want to minimize 6p squared plus 6p plus 3. So differentiate this, 12p plus 6 equal to 0. That is going to give us a minimum because we have 12 for the second derivative. So p is going to be minus a half. And I want to get, what is it? So I want to get the greatest possible value of m. So this thing when p is minus a half. So what am I going to get on this then? So I've got 6 over 4 minus 6 over 2 plus 3. So they cancel. So I've got 1.5, and then I'm doing 1 over that. So I've got 2/3. That's going to be, it's not one of those answers. It better turn up. Oh, there it is, E. Okay. 11. So we're on to the second half. Sequence xn is defined by the rules x1 is 7, xn plus 1 is that horrible looking thing. The first 3 terms in the sequence are 7, 3, 1. What is the value of x100? Right. Yeah, I don't really know what I'm doing with this then. So is there going to be some kind of cunning relationship between these? We can write it out as a formula maybe. So I've got x1 is 7, I've got x2 is then 23x1 minus 50. I mean, I know this comes out at 3, but let's just have a look at it. 5x1 plus 1. So x3, now this is not going to give a nice, what I was hoping it might be, I don't know, I mean, you can see how ugly this thing is. But I said, well, if I did this and say that was what x3 is in terms of x2, and then put this x2 in, but you're just going to get this horrible nested thing because x2 is so complicated. Putting all of that fraction in for that x2 and then again there, yeah, I don't see that cancelling down or anything nice. Maybe look at more values. Is this just going to loop round or something? X4 is going to be 23 times x3, which is just 23, minus 53 over 5x3, so 5 plus 1. So that is what, minus 30 over 6. So that's minus 5. X5 is going to be minus 5 times 23 minus 53 over minus 25 plus 1. So that is minus 115, 168, minus 168 over minus 24. So that's what, 7? Oh, we come back to the start. We have come back to this. That's definitely 7, isn't it? 140 and 28, 168. Yeah. Right. So we come back to the start again. So we're going 7, 3, 1, minus 5 over and over again. So if we want to get up to 100, we'll be on a minus 5 because that's a fourth one in the sequence, isn't it? 4 goes into 100, so it must be A. It must be minus 5. Okay, that was a fiddly sort of one. But if in doubt with series, you just look at them and see, you know, what's going on. Just keep bringing out numbers until something spots as a pattern. Right, question 12. Anyway, polynomial function f of x is such that f of x is greater than 0 for all values of x. Given that the integral of f of x dx is a between 2 and 4, which of the following ones must be correct? Right, so I've done a whole load of translations here. Right, so they've added 1 onto all of them. So if they've added 1 on, all of the gaps are 2 in the limits. So that's going to do a plus 2 on stuff. These are just translations. And so if we can get A, if we can get the same A, so we've moved it 2 to the left, so a 2, 4 become a 0, 2, and a plus 2. So it's going to be B, isn't it? Let's just double check that all of that's right. So we take f of x, we move it 2 to the left, as we've done in all of them. So we can make that a 0, 2 on the limits. That will give us A. And then we've moved everything up 1. So that just gives us a rectangle at the bottom of whatever we integrated before of 2 by 1, which gives us a plus 2. Yes, so it's definitely B. Okay, that was a nice one. 13, in the expansion of that, the coefficient of x to the 4 is 8 times the coefficient of x squared. Given a and b are non-zero positive integers, what is the smallest possible value of a plus b? Okay, so right, we only need to go up to 5 on this then, so let's get a bit of Pascal out on this. So that's 2, 3, 4, 5. So we're on this one. So if we've got an x to the 4, so we're going to have a 5 there. So we'll have 5 lots of b to the 4 and an a. So that's what we've got for our x to the 4. And then for x squared, we're going to have a 10. So that's going to be a 10. And we've got a b squared and an a cubed. Okay, and the coefficient, this one is 8 times that one. So we multiply that by 8 and set them equal to each other. So 5b to the 4a is 80 b squared a cubed. Right, so a and b are non-zero positive integers. Excellent. Get rid of those and that. Get rid of that and that. So, well, I can get rid of that, make that 16. So I've got b squared is 16a squared. So b is 4a. And I want the smallest possible value of a plus b. Right, so b, they're non-zero positive integers. Right, so they're integers. So the smallest we could have for a, so if a was 1, b is 4. So they're going to add up to 5, which is C. Okay. 14. The solution of the simultaneous equations that and that is x is p, y is q. Find the value of p minus q. So I'll make a couple of substitutions, I suppose. So I'll say, let's say a is 2 to the x, b is 2 to the y. So this will be a plus 3b is 3. This will be a squared minus 9b squared is 6. So, well, this thing's given us 9b squared is going to be 3 minus a squared. So a squared minus 3 minus a squared is 6. A squared minus 9 plus a squared, that's handy, minus 6a is 6. So minus 9 plus 6a equals 6. A is 15 over 6, which is, well, 2.5. So I'll say 5 over 2. B is going to be equal to 3 minus 2.5, so a half, divided by 3, so a sixth. So I've got that 2 to the x is 5 over 2. So x is log base 2 of 5 over 2. 2 to the y is 1 over 6. So y is log base 2 of 1 over 6. And I want what p minus q, which is essentially x minus y. So why would they bother with p and q? Oh, I suppose it's a specific solution, isn't it? We've got x and y in these separate equations. P and q are the, yeah, what x and y are at the intersection of those. So yeah, they are different, I suppose, in concept. So I want to do x minus y. So I want to do log base 2 of 5 over 2 minus log base 2 of 1 over 6. So that's going to be log base 2 of 5 over 2 times 6. So, because I'm just going to be dividing by that, aren't I? So it's going to be 15. Log base 2 of 15. F. There we go. Never like it when they have it as the last answer. I always think it's not going to be there. But fortunately it was. Right, 15. He's given that f of x is that. Consider the following three curves. Y equals f of x, y equals f of x plus 1, and the curve y equals f of x plus 1 reflected in the line y equals 6. Trapezium rule, yawn, is used to estimate the area under each of these three curves between x is 0 and x is 1. State whether the trapezium rule gives an overestimate or an underestimate. Okay, so we want to go between 0 and 1. So what is this thing just generally looking like? It's going to be going through 10 at 0. It's a negative quadratic. So when we get up to 1, we're still positive, aren't we? So we're going to be at -8. So it's doing, well, we're going to have a root here at root 5. So we're a way off hitting that. We're just looking at this bit, say, up to 1. So that's going to be an underestimate for the first one. Then if we're moving it 1 to the left, it's still going to be, well, it's still going to be in this bit because we haven't hit the root. So it's still going to be an underestimate. And then we've moved it across and then we've reflected it in the line y equals 6. So it's then going to be like this. So it'll be an overestimate. So we want under, under, over. Under, under, over, which is B. Oh, I like those ones. You know, I don't like seeing trapezium rule, but when trapezium rule is just for whether you're getting underestimate or overestimate, then it's not as bad. Right, so the functions f and g are those. What is the complete set of values of x for which one of the functions is increasing and the other one is decreasing? Right, so f dash is going to be 6x plus 12, and then g dash is 3x squared plus 12x plus 9. Okay, so we want one of them is increasing and the other one is decreasing. So, well, let's look at this one first. So f is increasing when, so we want this thing to be positive, so we need to be x is 0, so x is greater than equal to -2, and it's going to be decreasing if x is less than -2. Right, so which way round are we going to do on these then? Do I want to, I mean, this thing, does this factorize? We've got a 27 and a 12. Oh, it's just going to be straight 9s and 3s, isn't it? So that's going to be 3x plus 9 and then a x plus 1. Yeah, that works, doesn't it? Okay, so do I need that? We need this to be, so if this is increasing, we want this to be decreasing. Oh, this is so much to blink and take in. There's too many permutations here. So if this is, oh, good grief, right, so if this is greater than or equal to -2, so if this thing's increasing, we want this to be decreasing. If it's greater than or equal to -2, this one's still, it's going to be positive regardless. So we still need that to be negative. So we can't go as far as -1. So we need to, well, we can go as far as -1 and then we're stuck with it. So we need to be between -2 and -1. That's what we need for that one. Okay. And then for this one, if it's decreasing, we need this thing to then be positive. So they're both going to have to be negative because this thing, the second bracket's going to be negative regardless. So this thing's got to be negative as well, but we haven't got that far yet. So this is going to have to be less than or equal to -3. Okay, so I need that and that. Is that E? So less than or equal to -3 and between -2 and -1. So okay, E. Right. God, that was a bit of an annoying one. Two functions f of n, g of n are defined as follows. Right. What is the smallest positive integer n such that g of n is greater than 150? Right, so what are we doing? So we're integrating something here. Okay. And then we're adding up all of those integrals. Right, okay, so let's have a look at some of these fn's then. So when n is 1, f1 is going to, because that's where we're starting here, we're starting at 1. So that is going to be integral from 0 to 1 of 1 minus x dx. Okay, so that is going to be x minus x squared over 2, 1, 0, which is going to be 1 minus a half, which is a half. Okay, f2, that would be the integral, well, we've got a half of the integral from 0 to 2 of 2 minus x. Okay, so this minus x malarkey is not changing at the end, except we've got a half going on there. So we then get an x squared over 2. How is that? I don't know. Let's put it actually in and see what happens. So I've got 2x. I remember this half here all the time. 2x minus x squared over 2, 0 to 2. So that's a half of 4 minus 2, which is 1. Right, so we've gone half, we've gone 1. Let's look at another one, see what the pattern is. Is it going to go to 2? That'd be quite nice. F3, so if I was doing this for 3, I'd be getting a third, and then I'd have a 3x, so that'd be a 9, minus 9 over 2. So that's going to be 4.5 divided by 3, which is 1.5. Right, we're going up in halves. So I've got to add all of these up. How long is it going to take to get to 150? Right, okay, so 150. So that means I'm going to have, yeah, so this is doing, we've got this arithmetic. How many terms am I going to have on all of this? So I'm going to be doing the number of terms times a half, because I'm doing an a plus d type affair, aren't I? So I'm going to have the triangular number of d. I'm going to have n lots of a, so I'm going to have n over 2. I need to do the triangular number of d. So this is going up to, well, 1 less than n. So that's going to be an n minus 1. Because, yeah, d, the number of terms, we don't have a d in the first term. So if we're doing n terms, counting up there, we're going to have n minus 1 n minus 1th triangular number, which is n minus 1 times n over 2, multiplied by a half, which is our difference. So I need to solve this for n. So let's multiply by 4 to get rid of all of these halves. So 600 is 2n plus n squared minus n. N squared plus n minus 600 is equal to 0. Okay. Well, I'll say okay. It doesn't look that great, does it? I'm just going to go into this n squared. Well, it's not as high as 25, is it? Because 25 is too big, because you're going to have 650. 24 is going to hit it exactly, isn't it? Yeah, 24 squared, 576, plus 24 is 600. So 24 does it exactly that it comes out 150. So we're going to have to step up to 25 in order to get to the next number up. Oof, yeah, they're certainly ramping up, these numbers now, these questions. The graph of y equals log base 10 of x is translated in a positive y direction by 2 units. This translation is equivalent to a stretch of factor k parallel to the k-axis. What's the value of k? Right, so our base graph then of this is, well, it's going to go through 1, and it's going to look like that. That's our log graph. So we're moving it up 2 units. 2 units. Okay, so we want something which is here at -2, and then that's going to be the stretch that we're going to have on it, isn't it? Yeah. So, well, down there, so we want -2 is log base 10 of x. So x is going to be 0.01. So that's our 0.01 there. And that is going to be our stretch to go from 1 to 0.01, because that will move up and be going through there. So it's just going to be A. Again, translation questions are always the easy ones, I think, on maths papers. Anyway, question 19, 2 to go. A set of solutions to the inequality that is the interval that, where everything's real and C is less than 0. Right. In terms of P, Q, and C, what is the set of solutions to the inequality of that? Oh, it looks very similar, doesn't it? Looks very similar. I mean, is this another transformation? Is it another? It might be, you know. It does look like it might just be another transformation. Because if I divide by C squared, it does look like, yeah. Okay, so let's divide this by C squared. So C is less than 0, so I can divide by it. C squared isn't going to change the inequality sign. So yeah, let's try that. So I'll have x squared over C squared plus B x over C plus C is less than 0. So this is just, it's taken x to x over C. So I've got that P, x is between those. So x over C instead. So I'm going to have a CP and a CQ. So x will be between CP and CQ. Oh no, it won't, because C is negative. So if I've multiplied by the C's, yeah, so I've gone from this to multiplying by the C's, so I've got to flip the signs around, haven't I? So I'm going to end up with x is greater than CQ. Oh dear, I've forgotten that right now. CQ and less than CP. Okay, so does that fit with these? That looks like, oh, I've written in QC and PC. So D. Okay. And the last one to wrap things up, the lengths of sides QR, RP, PQ in triangle PQR are A plus D, and A plus 2D. Right, where A and D are positive such that 3D is greater than 2A. Oh my word. Right, what are the full ranging degrees of some angle? Right, so I need to get a sketch of this then. So I've got a triangle with 3 different length sides. So let's do a side there, a shorter side, and okay, I think that's meant to be the long one that I've done there. So let's say that one's A, that one's A plus D, that one's A plus 2D. So the one that's A is going, so that's QR, so that's Q, that's R, that's P. That fits, and it QR is A, RP is A plus D. Yeah, okay, so I've got the drawing. Then I've got this inequality. What is the full range in degrees of possible values for PRQ? So I want this angle. What can that possibly be? Right, okay, they haven't given us very many options here, so that should help. So we can, well, we're really trying to see where this point's going to be, aren't we, on Q? So we could swing the A one around, we could swing the P one around. So what we could say is, right, say we had the, I'm going to draw this, I've taken up the best bit of the screen already. We could have a base there, that's our A plus D. Then we've got some like A thing here, which is moving around, something like that. And we've got this one here. This is the side. Q could be anywhere along that dotted line. And then for this one, we've got an A plus 2D. Now, D's got no upper limit on it, but we don't want it to go too far, because otherwise we're not going to get it. Like, if D's enormous, it's just going to be doing, this. It's never going to intersect with the other side. But we could have it doing, well, let's have it where it does intersect. So say something, oh, it needs to be a lot bigger than that because it's going over here. But that's another sort of sweeping arc. So what I'm trying to get at, I'm drawing that very well, really. A plus D. Okay, that's not going to work. I need more space to draw this. Let's scroll down a little bit. What I'm trying to draw is baseline A plus D. From here, we say, right, there's some arc of values, which is going to be of radius A plus 2D. And then from here, we've got some other arc of values, which is going to be of radius A. And where these things intersect with each other is where we can get our value for Q, or our position for Q. So what situations is that going to lead to? Well, we could just have a straight line. That could certainly work, couldn't it? Because we could have, so if we had R there, we had P there, so that would be A plus D. That would be A. And then what did we say about D? Does that work? Yeah, it does. 3D has to be greater than 2A. So we've got D is greater than 2/3 of A. Okay, so yeah, so that certainly works, because we could say, right, this would be A plus 2D. So we've got A plus 2D is equal to 2A plus D. So get rid of that and that, get rid of that and that. We'd say A is equal to D, which is fine. It fits with our inequality. So we could certainly have 180 degrees. We can have a straight line and everything works. So it's going to be one of the bottom two. And then we got the other situation then. So in the other situation, we're going to have an actual triangle. It must be at the limit. It must be at this limit where D is equal to 2A over 3. So what is that going to look like then? So we'd have a, so D is 2, so we'd have an A there for one side. We've got A plus 2D. So that's A plus 4A over 3, and then an A plus D. So that would be a 5A over 3. This would be a 7A over 3. Okay, so what does that mean then? Is that going to be, what does this angle look like there? Well, if it was 90 degrees, we'd be able to square these. So if we square these, we would have an A squared, and we'd have a 25 over 9A squared. And this is a 49 over 9A squared. So adding these up is just giving us 34. So that is less than, what does that mean? What does that mean? If it's less than, what side of the, so it's going to have to be going that way, isn't it? It's going to have to look like that, because this is too long. This side is too long to be a hypotenuse of a right angled triangle, is what we're showing here, because we've got a 49 over 9. That's a 34 over 9. So the hypotenuse is too long for it to be right angle. So it must be bigger. It must be 120, not 60. So it's not going to be D, it's going to be E. That was the best question in it, I think, that one. That was really sneaky. But still, that's the 20 questions. That was a nice paper. I enjoyed that. That was some fun maths. I had some difficult questions. 20 was great fun. 19 was possibly the closest one I had to really messing up, because again, it was nearly missed this C being negative at the end, but that was okay. What else have we got? 18 was pretty easy. Transformations. They had quite a lot of transformation stuff, didn't they? 17 was tough, I think. And 16. 15 was, I thought, for me anyway, straightforward enough. 14 was standard. Had some weird sort of ups and downs on it. I mean, that was a quick one in 13. 12 was really quick. 11 was unpleasant. It went quick, slow on this, really. I think the first few questions were pretty straightforward. Then they got quite difficult, and then they got easy again around the turn, and then they got difficult again towards the end. So yeah, it was quite an interesting paper all in all. I don't know whether paper 2 is that going to be different types of questions? Is it going to be more difficult? I don't know, but it'd be easy. It'd be interesting to see what comes up on paper 2 on the next one, because I don't know whether they do it by difficulty or what. But still, first exposure to a TMUA, and it was quite a pleasant one. So I'll be back with paper 2 in a video soon.